Thank you so much for everyone that's on the line for joining us today. We're so thrilled to have you for our Exploring the Moon webinar, um, the past, present, and future. We are broadcasting to you from the NASA Johnson Space Center in Houston, Texas. And before we turn things over to our guest speaker, I just want to make a few brief opening remarks. First of all, my name is Paige Graff, and I'm the lead facilitator of today's session. Also working with me is Suzanne Foxworth and Julie Fouché, who you'll notice might be interacting with you in the chat window as well. We want to welcome all of our participants. We have people that have registered from 37 states, from DC, from Puerto Rico, from Canada. We have librarians, museum staff, educators, solar system ambassadors. We've got a diverse group of people on the line who work with a variety of audiences. So we're so thrilled to be able to bring you to us here virtually so that you can learn about exploring our moon with our featured speaker, John Gruener. Now, before we turn things over to John, the one thing I think you perhaps are aware of is International Observe the Moon Night. And that's one of the reasons we are hosting this webinar today, is because International Observe the Moon Night is this Saturday. There'll be events all across the world that are happening. You can see my map on the right that shows just a smidgen of the different events that are literally happening all around the world. You can check out information on the moon.nasa.gov/observe website, but this is a fantastic sort of international event to help celebrate our moon. And so that's why for today's webinar, we're exploring the moon. For future webinars, we might talk about Mars or asteroids and many other things. And so our website is there for your information as well. So that's it in terms of my opening remarks, because I just wanted to acknowledge we appreciate your time, we appreciate your participation today, and we're really excited to be able to share with you John Gruener. So John, with that, I am going to stop sharing. I'll have you share your presentation, and then you can start to introduce yourself.
Welcome, everybody. Hope you're having a good day. Down here in Texas, we're really waiting for that first cool front that's going to get here next Monday, because we're still a little warm in the lower 90s. I'm kind of tired of summer. But I'm glad we're talking about the moon, because we're kind of busy right now at NASA. We've been asked to try to get to the moon back in 2024. Which is what, less than 5 years away. So we're working hard. We just, put out a solicitation for commercial delivery to the moon, because we're going to be doing this moon mission. It's called the Artemis program. We'll talk about that in a bit. But we're going to do this a little bit different than our parents and our grandparents did for Apollo. Whereas Apollo, everything was, government-owned spacecraft and rockets. We're going to be using commercial services. We've already started with robotic service delivery to the moon called the Commercial Lunar Payload Service, or CLIPS is that acronym. We love acronyms, but we want to do it with people too. So, I liken it to when I traveled to NASA headquarters in DC. I don't fly a NASA jet, and I don't stay in a NASA hotel, and I don't eat at a NASA restaurant, right? I do all of that commercial, and that's what we hope to be doing in space, and we're our first, real good try beyond Earth orbit will be the moon. So we'll talk about that, but first we'll talk a bit about the past, all right? And let's make sure I can do this. Yes. A little bit about me. I was born and raised right here in Houston, Texas. When I was in high school, so I graduated in 1979, just 10 years after Apollo 11. And I was talking to my school counselor about, well, what do I need to be if I want to work in the space program? And we came to the conclusion that aerospace engineering sounded like space stuff. So I went up the road to the University of Texas in Austin and got my first degree in aerospace engineering. Came back down here to work at NASA. I really wanted to, I heard NASA was talking about going back to the moon, even, back then in the mid 80s. But if I had to start off working on space shuttle missions, and then I worked, doing trajectory design and orbital mechanics, the stuff you learn as an aerospace engineer. And then I worked on putting together something called Space Station because we were talking about it. It hadn't been done yet, but now it's the International Space Station and it is all done. But at the very beginning, we had to do analyses to make sure that when we put, pieces together with the space shuttle and then went back home with the space shuttle, those pieces were stable up in space. Every time we left, we still had a stable spacecraft. So that was pretty interesting, but I was just biding my time till I could get onto the Moon Mars project, which I did. And my job was focusing on the lunar surface. What would we need on the lunar surface in the way of habitats for the astronauts to live in or vehicles for them to drive around in? And in order to, come up with the right set of things on the moon, we needed to talk to people who wanted to do things on the moon. And so the group I talked to were the scientists, the planetary scientists. And the more I talked to them, it's like, wow, this whole science thing is a lot more fun than the engineering thing I'm doing. So I went to night school right here locally, University of Houston Clear Lake campus. And me and about 8 other people, we worked with the dean to fashion a planetary science program for us using a lot of the NASA PhDs and also some of the local Lunar and Planetary Institute people. And ever since 1994 now, I've been working mainly in the science field. So what I like to tell kids in school is, we always tell them they can be anything they want, but that only works if you get a good basic education first. A good broad education so you understand a lot of things. You're not really an expert in anything, but you know a lot about, a little about a lot of things. And then as long as you have that flexibility within you and you're open-minded to try new things, you can do many things. It's all really up to you, right? And so when you are, doing the different jobs, whether it's engineering or science or, you're a writer or a teacher, when you're working at, I found in the design process, the most important thing in the design process is being imaginative and creative, right? Because if you just try to be very closed-minded, fixed mindset, well, we're going to design it like Apollo did, maybe things aren't going to work right? So be imaginative, be creative. And then when you're doing that, make sure you're spending your time on meaningful accomplishments and meaningful results and not just, playing around here and there and, you have your hands in too many different sandboxes, right? So that's what's helped me get through my career so far. I started in 1986. Here we are in 2019. So that makes me 58 years old. I hope to retire in about 5 or 6 years. But if we're going to the moon, like we're advertising, I may just stick around because I think it's going to be a lot of fun. The bottom pictures are some of, my career. On the bottom left, that's me at a pyroclastic flow in Los Alamos, New Mexico. It's a beautiful state if you haven't been out there. A lot of terrain features, very similar to what we see out there on planetary surfaces. The middle picture is in front of Colton Crater in the San Francisco volcanic field just north of Flagstaff. And Colton Crater is actually a Mare volcano. So magma was coming up, it hit water, the water flashed into steam, and there was a huge explosion. So it's actually a big volcanic crater, but it kind of looks like an impact crater. And then, like today, talking to you guys, on the right there, I visited a school over in Katy, Texas, just west of Houston. They had a whole crew of astronauts that were getting to do a Mars mission simulation through a whole weekend. They were going to spend the night in their gym, in their spaceships, and do all sorts of things. So I went and talked to them, and I even brought them a piece of Mars to look at. It's Mars meteorite, and we have about 60 or 70 of those. So that's kind of my career in a nutshell, and I've enjoyed the whole trip. And like I said, another 5 or 6 years, and then I'll turn it over to that younger generation. All right, so but what we're going to talk about today is the moon, because that's what's really most fascinated me. As a kid, I grew up watching the Apollo missions, and that was just fascinating. We didn't have a lot of money in the 60s and 70s when I was growing up in Texas, so many of our vacations were spent in state parks because it was very cheap. But man, so many things to see and do at state parks and national parks, all the exploring, it's maybe the first time I've ever seen it, but of course, plenty of other people had been there before. But to me, it was like exploring something new. And so I really wanted to work on these moon things. One of my motivations was my Uncle Don, the fella on the left-hand side in the dark trousers. He worked as a technician at the Johnson Space Center. And there's me in my cool little red tennis shoes. I was about 4 years old in this picture. So this is about 1965, right in the huge technology and development and design portion of Apollo. And what we're standing in front of is a huge thermal vacuum chamber where you put a spacecraft in there, close the door, suck out all the air and atmosphere, get it as close to a vacuum as you can. And then you can either also cool it down with liquid nitrogen or heat it up with lamps to simulate the temperatures from the sun. And just watching what my Uncle Don did during Apollo and looking at all the cool stuff in his garage when we would go over to their house really inspired me to join this space program, right? And here's a quote from Arthur C. Clarke. It comes from 1951. He wrote an amazing book called The Exploration of Space. And much of what is in that book was all true, factual kinds of things. A lot of people think of Arthur C. Clarke as a science fiction writer, right? But he also wrote a lot of science facts. So, he talked about telecommunications satellites in geosynchronous orbit and human missions to the moon and building space stations in low Earth orbit and flying space shuttles up into space. He talked about all this way back in the 50s. So it's a really cool book. It's called The Exploration of Space. And this one sentence basically sums up my career so far. The first part, the first sentence in black is all about engineering, that technical problem and the challenges that we're going to face to build the things to cross interplanetary space. But what I realized was, well, why are we even going to the moon? Or why would we even think about going to Mars, unless we're going to do something when we get there? And that's what science is all about, doing something once you get to the moon or Mars or any of the planetary surfaces in the solar system. So here's my career in a nutshell, thanks to Arthur C. Clarke. And he didn't even know I was going to be born 10 years later in 61. So that's pretty fun. All right. So those Apollo missions occurred in a 5-year span, 69 to 72. I was a second grader when the Apollo 11 landed. I was a fifth grader when Apollo 17 took off for the last time in 72. And the rocks and soils, about 840 pounds that the astronauts brought back, just completely revolutionized not only our understanding of the moon, but our understanding of how the inner solar system was, the planets in the inner solar system created. Because even though, technically our moon, I wish we had a real name for our moon other than the moon, because all the other planets, their moons have names. Ours is just the moon, right? But we know now it has a core, it has a mantle, it has crust. It went through planetary differentiation, just like Earth, Mercury, Moon, and Mars have all done, right? So the moon is in it, still giving us all sorts of interesting things tied up in these rocks and these soils. As our instruments and technologies get better, we're still learning new and more things about the moon. Now, 72 kind of ended our first US ventures to the moon, but the Soviet Union at the same time was flying missions to the moon. Their human missions never materialized. They had a huge explosion of their big rocket, very similar to our Saturn V. So their human missions to the moon never happened, but they flew a whole series of Luna missions. And the last one, Luna 24, was in 1976. And then it just kind of went silent. Nobody really explored, the moon or thought about the moon anymore. But we were busy trying to understand the moon from all the things that came back with the astronauts. Now, as y'all all know, or probably know, 2 of the astronauts went down to the surface. 1 stayed up in orbit. And one of the things that astronaut was doing was photographing the surface from orbit and also monitoring a whole scientific instrument bay, where we had a whole slew of scientific instruments pointed down at the moon. And as the moon flew over as the Apollo spacecraft flew over the moon, it was taking data below it. So at the bottom left, you can see the swaths of data that we acquired during Apollo missions, but you notice they're just around the equator, right? And they're not completely filled even, at the equator. And certainly in the upper latitudes, the higher latitudes and the poles, we don't really have any data. So we had this tantalizing orbital data that looked like something was going on there on a global scale, but we weren't quite sure. But that's the best we could do with Apollo because of the trajectories involved with the Apollo missions. We had to stay close to the equator. And of course, all of our landing sites, as you'll see in a bit, are all on the front side, so we could talk to them with direct communications. All right. Luckily, we're still getting samples from the moon every single year in the form of lunar meteorites. Right now, there are over 300 meteorites that have been identified as coming from the moon. We do this by comparing to the real rock, the rocks that we brought back from Apollo that are no kidding from the moon. I know earlier, while Paige was getting this set up, people are asking, how do we talk to people, to convince them we really went to the moon? Well, so we have those rocks that really came from the moon, and we can compare these meteorites to those rocks and convince ourselves they came from the moon. There on the lower right, you can see some useful web links. The people at the Washington University in St. Louis do an absolutely fantastic job with their lunar meteorite database. And the problem with the meteorites, though, is we don't know exactly where they came from on the moon, right? We know they came from the moon, but we don't know where on the moon. So it's really hard to tie a specific location to a specific meteorite. But sometimes we can say, well, it came from this region. We know it came from the bright highlands part of the moon, and we'll talk about that in a minute. Or it came from the dark Mare parts of the moon, right? But that's just the challenge of the meteorites. But what they did show us is many of these meteorites are much different than what we brought back from Apollo. And so if we just look at the Apollo moon rocks, we have a very biased understanding of what's going on the moon. And these lunar meteorites kind of expand it globally, so we can understand the moon much more like a planetary body. So here it is. I say 30 seconds. I don't know how long I'll spend on this slide, maybe a minute. But here it is in a nutshell. All right, so the moon's very old, 4.5 billion years or so. And we think it was formed when a Mars-sized body smashed into the Earth, and ejecta from that went out into a ring or a disk around the Earth, and then kind of came all together as the moon, as we know it. And so we know this by age dating the rocks that we brought back from the moon. And we all saw, and maybe you've seen in pictures on Apollo, that the surface of the moon is just completely covered by this loose, dusty material. On the Earth, we just say that's dirt, right, or soil. But on the moon, we call it a regolith. And so this regolith is everywhere. And in the older regions, it's thicker. In the younger regions, it's thinner. But it has parts and pieces of things from all over the moon, because the regolith is formed by impact. Huge impacts like asteroids, even small impacts like dust can help create this regolith. So, some scientists, that's all they spend their time on, is looking at this regolith from the planet. And when we go back to the moon in 2024 or so, and we're at the South Pole, we'll be at a brand new place, and we'll get scoops of regolith there as well as rocks, and see how that compares to our Apollo samples, right? So those dark areas, we're all going to look at the moon Saturday night, and for observe the moon night. And those dark areas up there, we find out, are just basaltic lava. Now, that shouldn't really surprise us, because basalt turns out is the most common rock in the inner solar system. Basalt's all over Mercury, Venus, Earth, Mars, and our moon. It covers our ocean floors, comes out of the volcanoes in Hawaii. It's a very, very common rock. So, it's kind of like, oh, well, that makes sense. There's basalt all over the moon. But we didn't know that until we went there and brought the samples back and actually measured them. Way, way back, Galileo and others, when they're looking through telescopes, these dark areas look very smooth. And so they thought they were seas. And in Latin, the word for sea is mare. So they called them mare, right? But then you started noticing there's holes in these mare, these craters. And if those are really seas, how can you have holes in the sea? So they're not seas, right? But they're a solid surface. And looking at the number of craters gives you a really good idea of how old or young a surface is. And it's pretty simple. A surface that has been around for billions of years and has been battered by impacts is going to have a lot of craters. A brand new surface that hasn't been around, for very long at all, is going to have very few craters. So you can simply look at different parts of the moon, count the craters, and kind of come up with your own relative age for the different parts of the moon. And just by looking at this picture, you can say, look, those dark Mare are younger than the bright highlands, right? We only had one mission land in the highlands. That was Apollo 16. And the rocks that came back were very feldspar rich. The moon's very much an igneous body because we think there once was a magma ocean, a couple hundred kilometers thick. And so as it cooled and minerals started forming, the denser minerals sank to the middle of the moon. The less dense minerals floated to the surface to make the crust. So the highlands are very aluminum and calcium rich. The Mare are very iron and magnesium rich. And that's kind of the moon in the nutshell. All right, so here's how the moon looks to our eyes. Now, of course, we only see the near side of the moon. That's because as the moon orbits the Earth, it's tidally locked. And as it spins on its axis, a lot of people don't realize the moon actually spins on its axis just like the Earth does. We have, 24-hour days because the Earth is spinning around. Well, the moon spins around on its axis also. But as it orbits the Earth and it spins on its axis, it always, has one side facing us, and that's the near side. The far side, we couldn't really see till we started putting satellites in orbit around the moon. And then we started getting images of the far side. And of course, everybody realized right away, wow, look, they're very different, the far side, the near side. How come? Well, we still don't know, but we'll talk about that in a little bit. And hopefully, when people come in to your museums and such, they're all educated and they talk about the far side of the moon and not the dark side of the moon, right? Because there really is no dark side of the moon. Like I said, the moon rotates and it goes around the Earth. So the sunlight moves across the moon's surface. That's why we have the terminator and we have the phases of the moon, right? So you have a near side, you have a far side, and the dark side of the moon is just a mythical thing, or it's a cool rock and roll tune from Pink Floyd. All right, well, here's how the geologists view the moon. All of these colors represent different ages. And, I talked about using craters to decide older and younger, but you can also use something called superposition, where newer features that are formed on top of older features kind of give you an idea of which is older and newer. So if you have a plain, say out in Kansas or even in Texas, right? And then over the years, a creek or a river cuts its way through the plains, those plains were there first and the river came second because it cut through those plains. And so we do the same thing with impact craters. So you can see the different colors craters on the near side. You can see some of these yellow, very youngest craters kind of splashed out across some of the older surfaces, some of the other colors like the reds and the blues. So this is called the superposition, where younger stuff is embedded on top of older stuff. So using superposition, using crater counts, we kind of had a general idea of the age of the moon, but we really needed those rocks to come back to, actually get real dates and times for those things, not just a general. All right, so Paige, I guess this is our first question. The Apollo missions were very successful. 1972 was the last time astronauts walked on the moon. Do you think the United States should send astronauts back to the moon? And if you say yes, why would you send them to the moon? So I think this is when Paige wants y'all to answer your questions in the chat window.
Absolutely. And you can either answer this as you're answering it, or think about the audiences that you work with and how you think they might respond to this, or common responses you've heard from others. And we're going to ask that you read in the chat. I certainly won't read everything that comes in. Read in the chat some of the responses that we see come in specifically to John's question here. And again, you can answer it as you, or thinking about how do you think the persons you work with or that you connect with may respond to this question. So this is just to sort of get a feel for how people think about this. And so I know we have some discussion going on in the chat, and we have some things coming in here, John, that as we read this, we can think about how people might be thinking about this. So I'm not going to read this. I'm going to read silently, and then we'll give it a couple of minutes, John, and I'll let you know when we want to sort of see what you think.
Yeah, I love this answer. Yes, we can use the moon for training. So the moon is a great place where we learn how to work and live off of the Earth. It's 3 or 4 days away by rocket travel. So what a great proving ground. If we're trying to live on the surface of Mars or, on asteroids or wherever, the surface of the moon's a great proving ground and training ground. Geology and astronomy. Of course, geology, yes. Along maybe 30 years ago, astronomers were more excited about putting telescopes on the moon, but at the time they had never done any space telescopes. And now that we've had the Hubble Space Telescope and all those other space telescopes, it's kind of fallen out of favor to do astronomy on the moon, except for a radio telescope on the far side of the moon, where all of the radio stations and TV stations, that we are constantly bombarded with, you're shielded from that on the far side of the moon, and it's just absolutely radio quiet back there. And so the astronomers still want to set up a big radio telescope on the far side of the moon. Let's see what science.
And John, I see another thing in there about people saying to support knowledge, learning more about things at the moon to be able to gain knowledge for future perhaps missions to Mars, which is another important point that NASA is trying to make now as well.
Yep. Like I said, the whole proving ground, and I like to see here, they're talking about how adaptable people are. Robots are great, but they have to be programmed to do everything. I know everybody's working on artificial intelligence. I really don't understand that at all. But I think it's, if I have, want to do something out on a planetary surface, I'm hoping a human's there to do stuff.
And perhaps someone even mentioned it could be a great retirement home. 1/6 gravity for those who might have some trouble getting around. That's an interesting point, eh?
Yeah, that would be great. People said, would you want to, go to the moon? Well, of course I would. And to tell you the truth, I would even be like a janitor or a cook or a dishwasher on the moon just to be there. I wouldn't even have to be a scientist going out on the surface. I would love to just go there and work for a while. I think it's going to be a fascinating place. Buzz Aldrin in Apollo 11, he called it magnificent desolation. And of course, that's a great name for it. All right. So let's move on. All right, because, oh wait, I guess I have to click here.
And it sounds like perhaps a lot of people out there, and hopefully their patrons as well, are in favor of a return to the moon, as we are as well.
Right, because, we're going to address that now. So here's something I typically do. Matter of fact, I'm going to do this at Rice University here in Houston on Saturday night for their Observe the Moon thing. Go out and get yourself a 6-inch cantaloupe. Get yourself 1.5 inch lime, separate them by 15 feet, and now you have the Earth-Moon system. The same relative sizes, the distance at that scale. And the neat thing about using those two things is you can eat them afterwards, or you use the lime in your adult beverage. But of course, you can also go around and around in a small classroom or in a small auditorium, all right? So the moon is much, much smaller than the Earth, but there's no oceans on the moon. We're mainly a water world, the Earth is. But there is no water on the moon, and there's as much surface area as almost all of North and South America combined. I mean, think of the Western Hemisphere, throw off about 10%, like, scratch off Florida, scratch off the, the little other peninsulas or things sticking out, the Baja Peninsula in Mexico. 90% of North and South America is about what's on the moon, right? So it's a huge, huge place. So let's look at this. Here's where we landed on the moon. You saw this in the slide when we asked the questions. Apollos 11 through 17, of course, we know 13 didn't quite make it, but we landed 6 times. So earlier people said, well, how do we convince people we really went to the moon? I always tell people, well, I could see why you think we faked it, a big Hollywood set, the dark lights, everything. But why would we need to fake it 6 times? Think about that. I know we have the rocks, right, to show that they're different from the Earth and that they came from the moon. But here's where we landed. And so keep in mind the distances between these stars and the angles or the geometry between the landing locations, right? And we take those landing sites and we put them in the Western Hemisphere, North and South America, right? So Apollo 16 right here in Houston, where I am, the farthest west we would have been is Apollo 12. The farthest north we would have landed was Apollo 15. Apollo 17 in Memphis, Tennessee, you know, maybe visiting Graceland and Elvis. Apollo 11, they're in the swamps of Arkansas and Louisiana, and that's it. So if you are supposed to be the expert on North and South America, and this is where you landed, what could you tell me about the Appalachian Mountains or the Rocky Mountains or some of those mountains on the West Coast, like up in Washington and Oregon that have little holes on the top of them and sometimes smoke comes out? You know, they're volcanoes. And we have those same types of volcanoes all along our West Coast, the West Coast of Mexico and the West Coast of South America. We all know now they're formed by plate tectonics, oceanic plate diving below a continental plate, melting, boom, volcano. If these, you know, 6 places is where we landed in North and South America, we wouldn't even have a clue that plate tectonics is going on this planet, right? And say you don't really care about rocks and dirt and plate tectonics, but you love biology. How much biodiversity would we have seen in these landing sites? You know, the Olympia Peninsula in Washington, the Everglades of Florida, the Okefenokee Swamp there in Georgia, and then the whole Amazon rainforest, right? So much more biodiversity in North and South America than that could ever be represented by these 6 landing sites. So have we been to the moon? You bet. Have we done the moon? No way, right? There's so many more places we can go, so many more science things we don't know. And so I'm really excited and hopeful that we get back in the next couple years with robots and people. Oh, speaking of robots, here's our next question. Robot technology has come a long way since the Apollo missions. Well, that's for sure. Do you think the United States should send robots to the moon? And then you have some choices this time. Before the astronauts go, with the astronauts? No, we don't need to send the robots, just send the people. Or D, both A and B. So let's see what you guys think about sending robots to the moon.
And again, think about this either personally or how the audiences you may work with might respond to this. What do they think about robots? Do they even realize a robot can just be a robotic spacecraft? So again, I won't read these answers out loud, but John, you can certainly follow along. And as we try to tell our student groups as well, thinking about the whys and explaining those answers really helps solidify some thoughts. So
I really like the answer from Brumby Elementary. Robots and astronauts have different strengths and capabilities. So, you know, our astronauts can only go out so often because those spacesuits are really tough to work in. You know, they're like pressurized bags because you're in the vacuum of space. So you have to fight to move your arm this way and then fight to pull it back in. You have to fight the suit to open your hand, grab a rock, and then close your hand. So it's a real workout in these spacesuits, and our astronauts can't be in them all the time. But robots can be out there quite a bit. Robots can go into more dangerous locations than maybe astronauts. We're going to talk about the South Pole of the moon and why we're fascinated with that right now. But there are these places in the South Pole that never see the sunlight, and they're very, very cold. Well, we would never send astronauts into that because their spacesuits couldn't handle those cold temperatures, but we will send the robots there. So really important partners, right? And I call robots an exploration bargain. And that's because, you know, at NASA, we have thousands of equations. Man, if you love math, come to work at NASA because we have all these equations to explain, you know, just about everything associated with space flight and planetary formation and geologic history. But the most, you know, important equation is really pretty simple. And that is mass equals money. If you want to send a lot of mass into space, like a human mission, you better have lots of money because, you know, those humans require life support systems to keep them alive and larger volumes because, of course, we are humans. So we need our volume. Robots are much smaller. You know, here's a picture of the Lunar Prospector spacecraft that went to the moon in 1998, and you can see it compared to a human, right? So much, much smaller mass with the robots than the spacecraft required for humans. So we save money there, right? Of course, we don't have to feed or water or provide air for these robots because, you know, they don't need any of that. So there's more savings. And we don't have to bring these robots home to their families, right? I know we get pretty attached to our robots, and when Spirit and Opportunity both finally died on Mars, that was kind of sad. But it's very expensive to not only go to some place, but then make sure you bring all of your propellant with you so you can get back home safely. You know, that was the big part of Kennedy's speech in the early 60s. People seem to forget that he said, and return them safely. They all talk about getting a man to the moon and before the decade, and then they do a cut in the soundbite. And really the most important part was bringing them home safely. Well, we don't have to do that with robots. So they're a real great exploration bargain for us. And actually 13 robots beat Neil Armstrong to the surface of, or to the moon, you know, before he did his little walk. We started with the Ranger spacecraft in early 1960s. NASA was still trying to figure out how to get things to the moon successfully. So you can see 6 of them didn't quite work, but 3 of them did work. And it looks like a big telescope. And that's because that's what the Rangers were. They would get closer and closer and closer to the moon and just keep taking more and more pictures until they smashed into the moon. And then, of course, no more pictures. But that's when we got our first up close images of the moon, but only at very specific points where they smashed into the moon. Then NASA created the Lunar Orbiter project, and 5 lunar orbiters then went in orbit around the moon and photographed places that the scientists were thinking we would send astronauts someday. And those were all successful, all 5 of them successful. And then finally surveyors, you know, we had all these pictures from orbit, but a big question was, well, if we land, it looks like the surface is pretty loose and dusty. Are we going to sink into just a dust bowl, and then our astronauts can't get away safely? So we had to prove to ourselves that the moon was hard and that we could land on it and walk on it. And that's what our surveyor landers did for us. And, you know, 5 of those were quite successful. They had a chemistry instrument that can measure the chemistry of the soil. They had cameras to show what it would look like from an astronaut's viewpoint. So all 3 of those robotic projects were very important to convince ourselves that, you know, we could go to the moon with orbital mechanics and all that, and then we could land on the moon and walk on the moon safely. So robots even played a real important, you know, part of Apollo, and a lot of people either don't know that or they just don't give it much credence, but they were so critical in the success of the Apollo missions. Like I said, the Soviet Union's last mission was 76, and then, you know, the moon just kind of went radio silent. People were still looking at it through telescopes. But the next mission didn't happen until 1994. And that was with the Clementine mission from here in the US. And that kind of set off a whole renaissance of a couple of decades worth of robotic missions to the moon. And you can see from this list, now it's not just the United States or the Soviet Union. A lot of other spacefaring nations started to get interested in the moon. And at the bottom, you can see the latest visitors are from China, the Chang'e 3 mission in 13, and then the Chang'e 4 mission, which is on the moon right now. You know, people don't realize that, you know, there's an active Chinese robot driving around on the far side of the moon. The first ever far side exploration. So we got to give China kudos for doing something nobody else has done. But you can see quite an interest in the moon from all the countries. And unlike Apollo, if you remember those images I showed you of the swaths of data around the equator, we put these orbiting spacecraft in polar orbits. So now they're going over the North Pole and the South Pole, and the moon is rotating underneath. So as you go over different parts of the moon, you get a new swath of data. I don't know if if you guys ever still make globes as a project with kids, where you cut out the little gores and then you use glue and you kind of make your own globe. Well, that's what we're doing with these data sets digitally. And now, instead of those tantalizing little swaths across the equator, we started to get a global idea of what's going on the moon. And if you look in the upper left corner of the near side, so that's an iron map. And you can see all the high iron in the white and the red. You know, most of our Apollo missions were in that area. But look at the rest of the moon that's so different from where the Apollo missions landed. You know, same with the titanium map. Or over, what's really interesting is this thorium map on the right. All of our, so thorium is one of these rare earth elements. It's an incompatible thing that doesn't really fit into crystalline structures very easily. And you can see that where we landed with Apollo on the near side was right in the middle of this thorium hotspot, right? So all of our samples are kind of biased by that creep, it's called potassium, rare earth elements, and phosphorus. You know, there's another NASA acronym for you, creep. But all of our samples were kind of biased by where we landed. And look at the far side, completely different from the near side, right? So these global maps started giving us a much broader view of what's going on the moon. And then here's some images of that latest visitor I told you about, the Chang'e 4 mission, still working. So it landed in January, and where it is on the moon, like most places on the moon, the terminator's moving across the moon, so you get 14 days of sunlight and then 14 days of darkness. And then the sun comes up in the east, and then you get 14 days of sunlight followed by 14 days of darkness. The really hard thing to do for robotic missions is to survive that lunar night, because you don't have sun hitting your solar rays to make electricity, and it gets very, very cold, right? The Chinese have made it through 8 lunar days, and now they're in their 9th. So very successful mission, and they're really learning on, you know, what it takes to work long periods of time on the moon, not just during the day while the sun's up. So here are a bunch of other missions that are kind of in the queue from all the different nations. In the United States, I mentioned we're looking at commercial partners to fly NASA payloads to the moon and then make some money in the process. You know, one of the driving factors for our exploration program right now is to create an economy out there in space. So more jobs will be created for people flying these missions, building these spacecraft to conduct these missions. And maybe someday, you know, when people are actually on the moon, tourists or hotels, you know, and again, when I go to Washington, D.C., I go stay in a Marriott or a Hilton, you know, maybe those Marriotts and Hiltons are going to be on the moon someday, right? So we're really pushing the commercial aspects of lunar exploration. The rest of these countries are mainly still focusing on their national space agencies, doing everything on the moon. But I think eventually commercial exploration is going to be a big part of what we do. And here are 4 of the companies that we're working with. Right now we have 9 companies that we're working with for commercial delivery. So, you know, you like to have competition. You like to have choices on who you can buy from. So we sent out task agreements, and then these 9 companies can choose or, you know, not choose to apply for a mission to the moon. And right now we have 2 of them on the books to land on the moon, I think in 2021, all right? So right around the corner, you're gonna see American robotic space companies landing on the moon with NASA payloads and other payloads from other companies or other national space agencies. So that's called the Commercial Lunar Delivery System, or CLIPS. All right, or actually it's payload system. This one says delivery service, because we're used to UPS or the Postal Service, or now Amazon Prime driving up into our driveway and delivering things to us, right? Matter of fact, in the upper left, the Blue Moon lander is actually part of a space company called Blue Origin, and Blue Origin is owned by Jeff Bezos of Amazon. So Jeff Bezos wants to deliver things to the moon, just like his company is delivering things all over this planet, right? So a lot of smart, creative entrepreneurs getting into this lunar exploration. All right, so here we are, back to the moon that we've been talking about, right? Here's what I like to refer to as the new moon. So remember, in Apollo, we landed on the near side, close to the equator. And so we know, mostly about those landing sites. We don't hardly know anything about the poles of the moon, because we only have orbital data. The far side, the Chang'e 4 is there, but that's it. And then what I like to talk about, the underground, because as a kid, I love going in caves here in Texas. And guess what? There are caves on the moon, all right? And we didn't know that until Lunar Reconnaissance Orbiter from our country took some really high resolution pictures, and we started seeing these holes in the surface of the moon, right? So we talked a little bit before about the difference in the far side and the near side. We don't really know why. You know, we've found from our missions that the crust of the far side is thicker than the near side. Maybe that's why the magma had such a hard time of getting up, you know, to the surface and, you know, lava spilling out. You look in the upper left corner, there's a far side, you know, there's a few dark areas of Mare or basaltic material, but by and large, it's that feldspar rich material all over the far side highlands, right? We don't know why. We'd like to go there to try to figure out why. But, you know, and remember, North and South America, you know, so you're looking at a whole continent's worth of territory there. Oh, the yard maintenance guys are outside the window, so I hope they're not making too much noise for you. Here are those caves on the moon I was talking about. Holes that, you know, penetrate the surface, and we see that you can actually go underneath these holes from our oblique images from the Lunar Reconnaissance Orbiter camera. Now, all of these holes occur in Mare regions, so lava regions. And so we're pretty sure these are lava tubes. We have lava tubes all over the earth. Maybe some of you, you know, people are near museums or in states that you have lava tubes. They're very fun to go into. And maybe they exist on the moon. And if they do, possibly we could live down in these caves, right? The moon has very extreme temperatures because there's no atmosphere to moderate it. Very extreme radiation, no magnetic field to block the radiation coming from the sun. And because it has no atmosphere, it's constantly being bombarded. Remember all those craters we talked about? So if you're living in a house on the surface of the moon, extreme temperatures, high radiation, constant bombardment, wouldn't it be nice to live underneath all that so you're protected, right? You don't want holes punched into your house, right? So some people think, what a great thing. We could live in these caves and be protected from all that and then go up on the surface to do our work. But we have very little information about these things other than these handful of images you guys are looking at. But someday they're going to be cool. I hope tourists get to go into these caves just like we do here on the Earth. Here's the ages, these modeled ages of all these lava flows all over the moon. And you can see it spans billions of years, right? So the oldest are around 4 billion. The youngest are modeled at around 1 billion. Everything we sampled from Apollo is kind of in that 2 to 3.5, you know, 2.5 to 3.5 billion years old. We have, you know, pretty old lavas in our Apollo samples and in our lunar meteorites. But we would really like to go to some of these warmer colors on this map, the oranges, the reds, the yellows, to get some of these younger lava flows to see if we can get a better understanding of the volcanic history of the moon. Matter of fact, one of those areas, the orange one that's kind of up at the top next to where it says LC, that's where the Chinese Chang'e 5 mission hopes to go next year. They hope to sample this very young lava and bring it back to the Earth and then age date it. And boy, then we'll get to, you know, get a better idea of the extent of that volcanism on the moon. Now, here's the most weird things, you know, we're talking volcanism on the moon. We don't understand these things at all. They're called irregular Mare patches, right? Because look at them, they're just blobs sitting there. And we're trying to understand, are there no craters on them or very few craters on them? So are they very, very young, or are they some weird form of volcanism that is very old, but when you penetrate it with craters, the craters don't stay, you know, intact? We don't really know. We have scientists on both sides of that fence, you know, debating whether they're very young or very old. So these really cool looking, you know, irregular Mare patches or imps would be a great place to go with robots or people to understand the very, you know, hopefully or possibly the youngest areas on the moon. But just, you know, they're fascinating to look at. We know from Apollo 17 where we collected orange soil. They called it orange soil, but what it really was glass beads that were created in a fire fountaining eruption. Much like the basaltic volcanoes in Hawaii have these fire fountains. Well, these glass beads are a great source of oxygen, and because oxygen is in that glass. Some of these glasses are hydrated. So, what a great resource if we can go to some of these deposits, chemically break out the oxygen, maybe get some of that water. And now I'm starting to mix in lunar science with lunar resource utilization, because people on this earth always have depended on their local natural resources to live off of, and it will be the same thing on the moon someday. And these pyroclastic deposits may be one of those resources we're going to go after in the future. But here's the resource everybody's really focusing on: water ice at the poles of the moon. Now, when they brought the rocks and the soils back from the moon, they didn't measure any water, right? And so we thought the moon was just cold and barren and dry. But as laboratory instruments have gotten better over the years and decades, we now are finding water in some of the rocks that came from the moon, but at tiny amounts. From our polar orbiting spacecraft, we look into these areas of the moon near the poles that never see sunshine. We're going to have a slide here in a minute that talks about the axis, the tilt of axis of rotation. So our Earth is tilted 23.5 degrees, and we have seasons. Thankfully, North American Texas is not pointing directly at the sun anymore, and it's cooling down finally. Well, the moon's axis is almost straight up and down to that ecliptic plane where all the planets go around. And so the sunlight at the poles goes right across the surface, parallel to the surface. So if you're in a hole, you don't get any sunlight, and so it's permanently dark. It's the coldest regions in the universe. We've measured temperatures down to about 20 Kelvin. So 0 Kelvin is absolute zero, right? 20 Kelvin we've measured in these craters, and some of them are showing properties of water ice or water frost on the surface. So again, what a great resource. If you're in the deserts of North Africa, what are you really looking for? You're looking for that oasis where you can get some water to drink. Same thing on the moon. We're in the lunar deserts. We have these oases at the poles. Now it is water ice. So we're gonna have to dig up the dirt and melt it to get the water ice. And unfortunately for us, it's a lot more complicated than just water ice, because there are all sorts of hydrocarbons and things like hydrogen sulfide that are mixed in with the water ice. So now, we're gonna have to figure out how to separate all of those compounds so we just get the water to drink and it's not tainted with all that other stuff. But this is a real hot topic, a cold topic in lunar science these days, and many of our missions and thoughts are in the polar regions to check out this water ice. All right, so here's your next question.
And John, not to disrupt you there, but we might skip this since you talk so much about the importance of water, just due to the time frame.
Sure.
So, I think
well, they can still put it in there if they agree water is the most valuable, and we'll kind of see, because there are all sorts of resources there for sure. But yeah, I can keep going.
Yeah, we've got about 5 minutes till the top of the hour, and I know you've got some other great information as well.
All right. So this slide here kind of, and so all these are recorded, and you can get these slides and use them. So you can see the moon's axis of rotation only 1.5 degrees. So you get these permanently shadowed craters where it's really, really cold, right? Here's a map of the PSRs in red. The larger PSRs are in red. The smaller PSRs are in the cyan color, if you will. And you can see they're all over the place. The challenge is, just because you have a permanently shadowed region doesn't mean you have water ice. Some of these permanently shadowed regions aren't showing any signature water ice. Some of them are, and we don't understand that, right? And this is just the very surface. What about below the surface? How much ice is below the surface where we can't sense with our science instruments? It's a very challenging and important question that we're going to be trying to answer in the next few days. Oh yeah, Paige, so I see you left a lot of these technical slides in. So here's a neutron detector. It can penetrate about 1 meter. So, so where you're seeing the purplish colors and the blues are the places in the poles where we can see water, or actually what you find with the neutron detectors is hydrogen. And then you make that leap of faith that most of that hydrogen is in the form of water, right? But you can see they're very localized and not spread out evenly everywhere. And so I was telling you about the water that is on the moon. We had a spacecraft called L-Cross, and it smashed into one of these permanently shadowed craters, created a big plume of ejecta out of that crater, and inside that plume were gaseous compounds. And look at this list of gaseous compounds. You know, so the water, luckily, is the most abundant compound. But all that other stuff, while it will be useful someday as a resource, if we're hoping to use the water to drink, I see in the chat, some people were talking about, you take the H2O, electrolyze it between oxygen, hydrogen, now you have rocket propellants, right? So it's a great resource, but it's not just there by itself. It's going to be a challenge to separate it from all of these other ices that are in those permanently shadowed craters in the pole. And of course, you know, so much on Earth depends on water, right? Our life, of course, does. Our bodies are mostly water, but also industry has used water. Civilization have used, you know, ports and rivers as places where people live. So it's going to be the same thing in space. Water is going to be so important in space for rocket fuel and life support and just all sorts of industrial things that will happen someday as we're learning how to use those resources on the moon. So how about this one, Paige? Do we have time to ask when we might send people?
This one's so quick, I think it's worth it.
Yeah, because I already mentioned it at the beginning of the talk. So we'll see if they were listening, if they can remember what year I talked about we're shooting for. Yep, there they are, 2024. Yeah, that's and hopefully, yeah, hopefully 2024, because it's you know, there's no guarantee we can get there.
And some folks aren't even aware of that either. So I think that's important to make sure folks are aware we're looking at 2024. You're absolutely right.
Right. So this is what we're being directed by the National Space Council and the administration. And these are the kind of words they gave us, you know, using commercial and international partners, long-term human exploration and utilization of the moon, 2024, the first woman and the next American man on the South Pole. Right. And that, of course, only works if the other countries don't beat us to the moon. Maybe China's going to have that first woman on the moon. Who knows, you know? But it's going to be great for mankind or humankind, you know, whoever gets there, because we're just going to, you know, constantly learn more and more. And the challenge, though, is just because the president says something, right? Congress doesn't have to go along with it. You can look through the history of NASA, and sometimes the presidents will propose something and Congress gets behind it, like the Apollo program, and it really happens. But sometimes the presidents will propose the space exploration program and Congress just kind of, you know, gives it a thumbs down or a lukewarm, doesn't give enough money. So we have to have both the president and Congress behind us to really fulfill the space policy of getting back to the moon in 2024. And we're calling this Artemis, all right? So I'm not real good with mythology, but from what I hear, Artemis was the twin sister of Apollo. So I grew up as the Apollo generation, and the kids growing up today are part of this Artemis generation. And it's not just about the moon. It's getting to the moon first, learning how to work and live on the moon, and as a training ground, proving ground, and then going to places like Mars and other destinations in the solar system. So it's the Artemis program. You can, you know, go to www.nasa.gov and read up on the Artemis program. I think it's a pretty cool logo. I like the colors they picked out. Here's a little graphic of what it might be like at the South Pole. The moon's low on the horizon, just like the sun will be low on the horizon. The shadows could probably be a little bit longer. Could be some other darker spots, but it's going to be a fascinating place to go. Here's a light map. So from LROC. So there's a great website. You go to the Lunar Reconnaissance Orbiter Camera or LROC website. They just have a treasure trove of images for the public. And this is an illumination map of the South Pole where the bright regions get a lot of sunlight. Like the brightest regions, you're getting about 80% of your time, 85% of your time in sunlight. The dark regions, black, no sunlight at all. Those are those permanently shadowed craters. And you can see shades of gray in between the very bright and the very dark. So we're using data sets like this to pick landing sites that we could go to and operate in the daylight and in the sunshine, but venture into those dark permanently shadowed craters looking for water ice, all right? So our main goal of all of this is really just to learn how to work and live on another planet. And Arthur C. Clarke said these very same words in his 1951 book, Exploration of Space, right? We got to learn how to work and live. The moon's so close. So why not use that as a proving ground and a training ground? And a big part of learning how to live and work on these planetary surfaces is how to use the natural resources and live off of the land. So we don't have to bring everything with us. Remember, mass equals money. If we have to bring all the mass we need to live there, it's going to be very expensive. If we can use the lunar resources or the Mars resources, so we don't have to bring so much mass, now we just made it that much more affordable for everybody. And then, like I said, you know, the moon is a great proving ground for spacesuits and life support systems and rovers and habitats. And it's 3 days away. If something goes wrong, we can either come home quickly or, you know, we can send things to the moon. Those Mars missions, we can only do those once every 26 months when the planets are in the right alignment. And so you just don't have the kind of opportunity like we do at the moon. So here's my my best imitation of Yoda. All right, I love Star Wars. And so close, interesting, and useful the moon is, right? I wish I could talk in a Yoda voice, but it's all of those things, all right? And I hope y'all got a sense of that. And it's just sitting there, patiently waiting for us. And hopefully in the next couple of years, you're gonna see more robotic missions getting to the moon. And then again, people around 2024 or so. And I think that's it, Paige.
We certainly hope that you've gained a perspective of exploring our moon in the past, present, and the future. And if it is the top of the hour, so if you do have to depart, we do hope we gave you some valid and great information for you to share with your audiences during International Observe the Moon Night. I do want to make sure I thank John Gruener for sharing his knowledge, his passion, and even his career path, which is so important for us to be able to translate and share with all of the folks that we may interact with, whether they're young or old. But with that, if you're able to stay on the line, if you have questions, you can put them into the chat window. And John, I'll start reading off some of the questions.
Yeah, I'll let you monitor the questions and you ask me the ones you think are asked the most or.
Absolutely.
So go ahead.
So, you know, one of our groups, let's see, had asked a question early on about, now, and I'm not familiar with this, but one of our solar system ambassadors was asking about hypotheses for the moon's formation and asked about the Sinestra formation hypothesis. I'm not sure if you're familiar with that and if you can provide any input or tell us what are the hypotheses.
What phrase did you use there?
Sinestra formation.
Nestra. Yeah,
Sinestra.
Sinestra. Yeah, I'm not quite sure of that term, but before Apollo, there were three classic ideas for the moon. One was that the Earth was spinning so fast that it slung off, you know, a part of the molten, gooey early Earth into space and from the equator region, because that was spinning the fastest. And that was called the fission theory. So that a piece of the moon kind of flew off of the Earth, or a piece of the Earth flew off and then turned into the moon. So that was the fission theory. Another hypothesis or theory was the capture theory. So the Earth's out there and the moon's flying by and it comes really close to the Earth and the gravity of the Earth kind of catches the moon and then the moon comes around again and it gets even closer to the Earth. And so the gravitational field of the Earth captured the moon as it came by slowly and closely. So that was called the capture theory. And then there was the co-accretion theory, where the Earth and the moon kind of formed at the same time in the same nick of space. For whatever reason, the Earth accumulated more mass, and then the moon started orbiting it. So that they kind of formed in the same neighborhood, or co-accretion. Once we got samples back from the moon and we started comparing them to rocks on the Earth, they kind of took some of those hypotheses or theories and merged them together in what we now call the giant impact theory, or I like to say the big whack. And that's the one where the proto-Earth is there and then a Mars-sized body comes and slams into the Earth. It throws stuff into space. It makes this disk that, you know, some falls back to the Earth, a lot falls back to the Earth, a little bit coalesces into the moon. And so that giant impact hypothesis is probably the favored one by many scientists, but I'm gonna have to look up Sinestra to see what that is.
Yeah, and I'll provide you with a link that someone put into and it's SYNESTIA. So I might have
Okay.
been mispronouncing that, or it was written in there in the original question. I read it as I saw it. So I'll give you some information on that, John.
Well, that's the cool thing about NASA. Every single day I learn something new. Um,
Absolutely.
Starting my life as an engineer, now as a scientist, of course I'm going to learn something new. But even though I've been in planetary science now for over 20 years, I still learn something new. So I'm going to learn about this Sinestra after we're finished here.
Exactly. So here's another question from Powerhouse Science Center, and they're wondering if you could address any major differences between NASA's plans for the moon and the European Space Agency's plans, if you can speak to that at all.
Okay, so Europe right now, ESA, European Space Agency, is very interested in the lunar resources. Matter of fact, right now they're having a workshop over in Europe on using lunar resources. And one of the small countries in Europe called Luxembourg is even trying to set itself up as that commercial connection to lunar resources. So very much interest in Europe on the resource aspect. They don't want to build their own big rockets and spacecraft to get to the moon, but they would like to partner with some of the larger space agencies. So, we're talking with them, just like on the International Space Station, ESA is a partner. We're talking to ESA and other agencies to partner with us on our missions to the moon. China is also talking to these nations to partner with China as China goes to the moon. Just today, at space.com, I was reading an article and seeing images of the Chinese manned spacecraft. It kind of looks like Apollo, but if you go to that and look at it, they're serious about getting back to the moon, or with more robots, but also sending people there. And so Europe can kind of pick and choose who they want to partner with, but they're very much interested in the moon.
Excellent. And that brings us to our next question, which is related to resources from the U.S. Space and Rocket Center. Kevin's wondering if there are any commercial partners lined up to develop lunar natural resource extraction for use on the moon, or to even export to Earth, if that's even a thought at all.
Right. So, I don't know if lined up is the right term. At NASA, we have things called Small Business Innovative Research Grants, or SBIRs. And so, there are companies out there with SBIR grants working on small excavator demonstrations, or small, demonstrations to concentrate sunlight into a little oven so that you can cook the oxygen out of the moon dirt. So we do work with small companies that way. There's something every year called the Space Resource Roundtable. Sometimes it's at the Colorado School of Mines in Colorado near Denver. Next year it's going to be up in Canada, where they partner with the Planetary and Terrestrial Mining Science Symposium, right? So at those venues, all sorts of commercial people come and talk about the things they're working on. But of course, you need that transportation system to get those excavators and those processors to the moon. And so that's what we're really focusing on right now, with both our commercial rockets and commercial delivery to the moon, in our Space Launch System, which is a really big rocket that will fly here in about a year or so. So we're working real hard on that delivery system, and then these smaller private companies are working on excavators and processors to go after these resources.
Yeah, and living off the land and utilizing those resources is a pretty important aspect. So here is a question from Duxbury Senior Center and Charles, who would like to know, so would most human lunar exploration be concentrated on the poles because of that availability of water or water ice?
Well, that's kind of what we're guessing right now. But the key word you just said, Paige, was availability. Just because we've measured water ice at the poles of the moon, and just because we might send some robots there and, confirm that, yes, there is water ice in these deep, dark craters, it's still in the deep, dark crater. And so we can't live in those cold temperatures in those permanently shadowed craters. So we have to live up on the peaks or the ridges where the sunlight is. And so maybe, you know, it turns out it's not going to be economically wise or viable to go and mine this water ice. It has to be there first, you know, in usable quantities, in large usable quantities, but then it has to be accessible and extractable, you know, in reasonable economic terms. Because we could just ship water from the earth, and launch costs are going down because our entrepreneurs are learning how to reuse their booster rockets. You know, maybe you've seen like SpaceX, where they go up in space and then they land their boosters right back on the earth so they can reuse them. Well, that's bringing down the launch the launch costs. So maybe someday, who knows, the launch costs might be so low, it would be just as cheap to send water and other consumables to the moon than to mine it in these deep, dark, you know, steep-sided holes. And so we won't know, of course, any of this until we try. Until we send our first robots to the South Pole, we send our first humans to the South Pole. Some scientists think that even in the sunlit areas where it's nice to live, if you just go down a meter or so below the surface, you're going to find ice, you know, almost like permafrost down, you know, below the surface. Right now, none of the scientific instruments that we've used have sensed very deep into the surface. L-Cross, when it impacted the moon, it excavated down to about 5 meters. And, you know, the percentage of water that came out was somewhere between 5 and 10 weight percent. So, you know, it may be that we have to dig down 5, 10 meters to get the real mother lode of water ice. But that's expensive. You got to get rid of all of that overburden. Now that dry soil, you got to get it out of the way so you can get to the icy soil below. So if it's available in an economically and you know, sensibly extractable way, we certainly will use it. But we got to see ourselves, you know, if it's a viable resource. It's there, but you know, does it really make sense to use it? And we'll only know once we get there and start trying.
Absolutely. So a few more questions here, and this one is interesting, and I certainly wouldn't be able to answer it, from St. Charles Parish Library, and they're wondering if there was ever a real concern about the moon being made of antimatter.
So I'm not really a physicist, right? Antimatter, I've never heard that. No,
Yeah, and I know
you know, you bring the rocks back from the earth, the moon, and they're very similar to the rocks on the earth, and we're not made of antimatter here, I don't believe. But yeah, that's way out of my ballpark or wheelhouse to understand. And I never heard that the moon is made out of antimatter. I'm gonna have to put that one down with Sinestra to see what people are thinking.
Yeah, and and like I said, it was a question and I wasn't quite sure if it was my lack of knowledge to be able to know how to address that. The only thing I was thinking is how you talked about how we weren't sure that the moon, you could actually land on it and stand on it or just sink into it because of the regolith. But okay, we'll call that one a bit of a mystery.
Yes, a big question mark.
Yeah, so here's one from a solar system ambassador who's wondering about, and from Brumby Elementary, asking about if it's feasible to extract helium-3 from the surface of the moon.
Well, it is. So since the moon has no magnetic field, the solar wind just constantly hits the surface of the moon. And those chemical elements in the solar wind, all of them get embedded in the lunar surface. Now, near the equator and during the day when the temperatures get hot enough, these solar wind particles then, you know, come out of the surface of the moon and they're lost, but many times they're embedded and they stay there. And hydrogen and helium are a huge part of the solar wind, and helium-3 is what we, you know, typically have here on the Earth. But helium-4 is another one of those isotopes coming from the sun. And, you know, they've done some measurements and indeed you can extract helium, helium-4 is on the Earth, helium-3 is on the moon, sorry. But indeed you can extract that helium-3 on the moon. Now you have to mine a large area of the moon because it's, you know, in very small amounts, but we could accumulate helium-3 from the moon. The challenge is helium-3 is mainly useful for nuclear fusion reactors. You know, theoretically, people think helium-3 would be a very efficient fuel for fusion reactors, but we haven't figured out a way to make fusion reactors work, right? So before if I was in charge of a lunar exploration program, I wouldn't worry about helium-3 right now. I would say, well, let's wait until fusion reactors are a reality, and then let's think about helium-3 on the moon. I think I would go after the water and the oxygen and the metals first, because those are known quantities and we know we need those today.
Awesome. Now, do you have time for maybe 3 more questions?
Oh yeah, I'm good.
Okay, good. So here now, a question kind of came in terms of any signs of microbial life. Have we ever found any signs of microbial life, whether it's been on surveyor landers or Apollo 12 or even in any rocks? Have we ever found any signs of microbial life from the moon?
From the moon, yeah, not that I know of. I've never seen a paper. I've never seen a presentation on microbial life. But we're talking about the poles of the moon, right? Where you have hydrocarbons and ices in these permanently shallow regions. So who's to say in those hydrocarbons? You know, you have all of the, the CHON or the CHON, carbon, hydrogen, oxygen, nitrogen. You have those things in these ices in the permanently shadowed regions of the South Pole. They came from comets or water-rich asteroids or, the interior of the moon. We don't really understand that. But possibly with that unique environment of the polar regions on the moon and with all that mixture of ices, maybe microbial, but nothing yet. And matter of fact, it's that sterility of the moon that really gets people who want to test for life on Mars. It gets them excited, because you build a contraption to look for life, you send it to the moon where we know there's no life, and if you come back negative, okay, great, my instrument's ready for Mars because we solved any contamination issues of human life in our instrument, and we're not getting any false positives, so it's ready for Mars. If you send something to the moon and you're looking for life, and all of a sudden you find all sorts of stuff, you probably have a contamination problem, right? So no, right now there's an office in NASA called the Planetary Protection Office, and they're very much interested in this, idea of protecting different planetary environments on different planetary surfaces. And on Mars, they have quite a few special regions and contamination control issues for any spacecraft that's going to Mars that, agencies or anybody who's trying to get to Mars are going to have to follow protocols to make sure you're not contaminating on Mars. There are no protocols for the moon right now because we just absolutely have no evidence of microbial life or any sign of amino acids or enzymes or anything like that on the moon yet, right? Again, these polar regions are very unique, and who knows what we're really going to find.
Right, and certainly that question of life is one that's certainly of interest across our solar system, and so the more we investigate, we shall see what happens.
Yep.
So here's a question from one of our JPL folks wondering, what's your opinion on some of the sort of, or perhaps the single biggest technical hurdle to a successful Artemis program?
Well, I think it's pretty obvious. Our biggest technical hurdle is trying to protect anybody living on the moon from the extreme radiation. Not only the solar flares or the stuff getting ejected out of the sun and coronal mass ejections, but the galactic cosmic rays are everywhere, and they come in very fast, and we don't really have a good way to stop those galactic cosmic rays. Now, another useful thing that people are talking about water is you have a water shield, and you use that water to slow down these energetic particles so they don't, pass through our bodies and cause damage. I like to tell people, think about it this way. I just mentioned the solar wind is a lot of, hydrogen or helium. So, something this big. And so what, moving really fast, what better way to stop something this big than with something the same size, right? And water has two hydrogens. So it's like a billiard table. All those little balls are like little hydrogen atoms, right? And if one billiard ball hits another billiard ball, you slow it down, and some of that energy goes into the other ball, but it's not moving as fast anymore. That's really what you're trying to do in radiation, is slow those particles down so they can't do damage. But if you have a bowling ball sitting on that pool table and a little cue ball comes into it, it's just going to bounce right off. It still has the same energy, the same speed, but it's just going the opposite direction. That big bowling ball didn't absorb any of the energy to slow down that little cue ball, right? So protecting us from radiation is huge. And if we're really going to stay there for long periods of time, we're going to have to figure out how to do that. I talked earlier about those caves on the moon. That would certainly be one way. You have tens of meters of rock in between you and that radiation, and it's not going to get to you, right? But we can also just simply bury our habitats on the moon. Even at the polar regions, we can dig trenches, we can put habitats inside and then cover them up to protect from radiation. So that's, to me, that's the number one issue for any long-term human presence on the moon, is solving that radiation challenge.
Yeah, and maybe some of those caves will help out too. Maybe there'll be some of those available for some of that help. So John, here's since we are the Rocks from Space people here at Astromaterials, we had a question from one of our folks there at JPL who was wondering, how would you answer this question? So if you had a moon rock in your bare hand, and we here would never hold a moon rock in our bare hand, but just saying, if you had a moon rock in one hand and a rock from your backyard in another, what are some of the noticeable differences you would point out to students? How homogeneous would you say moon rocks are compared to the diversity of Earth's geology?
Well, that would be a real challenge because, like I said, the rocks are very similar. The basaltic rocks on the Mare regions of the moon kind of look like the basalt coming out of Hawaii. So that would be a really tough one. I guess the way that I would probably do it most is, most of the rocks that came back with the Apollo missions are what we call breccias. And breccias are basically one rock made up a bunch of smaller rock fragments, and they're all held together by melt, impact melt, right? So something smashes into the moon, it throws some rocks up, and the impact melt kind of puts some together, and now you have it here. And then maybe a billion years later, something smashes again in that same spot, more pieces get glued together by impact melt. We don't have these, breccias like this so much on the Earth. We have conglomerates and rivers, and I guess we do have some breccias in our magnetic system, but just the nature of those lunar breccias is somewhat unique. What you really have to do is get into the lab and measure isotopes and things. The neat thing about the meteorites that we find down in Antarctica and other places, if they're not weathered too much, and see, that's another problem. Here we're on Earth with a very active geologic system. So weathering and erosion, changes rocks, constantly and quickly. Out in the deserts by JPL, most of those rocks are covered by something called desert varnish, and you crack them open and they look completely different on the inside than the way they look on the outside. So, on a meteorite, we have this fusion crust. As it's coming through the atmosphere, you're melting a thin outer layer of that rock and creating this fusion crust. And I've never collected meteorites. I'm not a meteorite guy. But what I've read and what I've seen is some of the fusion crust of the moon kind of has a greenish look to it. I don't know why. Maybe it's the olivine. So, if you have a really fresh moon rock and it came as a meteorite, then you could look at that fusion crust and say it's lunar. But really, it takes really good detective work in the lab to prove, meteorites come from the moon and to prove this rock's from the Earth and this rock's from the moon. It's real from the Earth and from the moon. It's really hard just to do it visually because those rocks are so similar. And and that gives credence to some people who think Mars smashed into the Earth. A lot of the Earth got thrown out there into space, and then became the moon. And so you had the same reservoir of stuff that made the rocks on the moon that we now have rocks on the Earth. And we don't see very many granites. So we do see granites on the moon, and very, very small amounts. We don't really see them like we do here on there. Most of our continental crust, right, is full of granites. But yeah, that's a tough one. And sadly, I don't think there is a way to have a moon rock and a Earth rock and visually see a difference. And you can, Paige, so we wouldn't let any of our Apollo rocks be held in a hand, but there are a lot of lunar meteorites for sale out there on the open market. And anybody can go and buy a lunar meteorite. They're a bit pricey, but now you have a moon rock that you can actually hold in your hand. So I don't know how much money these museums and educators have, but if you ever want a piece of the moon, go buy yourself a meteorite, and now you can hold it in your hand and not worry about the contamination because it's been sitting on the Earth for thousands or even millions of years.
That's right. And our moon rocks that we use here, we totally use them for scientific purposes. So they're never touched with a bare hand at all. But depending on the research a scientist may do, they've got to be able to say what they're going to do with that sample, because these are certainly precious resources that have really helped us know about and better understand our moon. So, but that's an interesting question. And we do want to encourage kids of all ages to go out, look at the rocks, look at geology, think about what everything around you is telling you, because rocks really do have a story to tell. And we find that pretty fascinating.
Yeah, I mean, that's how we are understanding the rocks and minerals we're measuring on Mars, with Spirit and Opportunity, and now Curiosity. One of my, times in life for about 4 years, I was working on building up a big database of known rocks and minerals here on the Earth that we think we'll find on Mars. And we do all sorts of measurements, and particular measurements wind up with reflectance curves. It's almost like a squiggly line of your fingers. And so what I always say is we get all these squiggly lines of known rocks and minerals on the Earth, and then we go to Mars and we find a rock and we put it in our computer database, and there's the match. And we did that with things like jarosite. We found jarosite on Mars. That's a sulfate rock that only forms in the presence of water. Hematite, goethite, all these minerals that we know form in the presence of water on the Earth, we have found on Mars. But if I was holding a jarosite from Mars and a jarosite from the Earth, I don't know that I could tell them apart.
Awesome. Well, John, I think I have gone through all the questions, at least in our Q&A area. So
okay.
Some of our folks have said, some of the things they asked about, they've heard somewhere else, like even this whole idea of, was life ever found or brought back? So, these are, I think these points that we've been able to chat about today give our folks on the line some information from a scientific point of view of what we know and how we know it, and all the data that you've shared, I think, can help hopefully enrich their abilities to share more about the moon with their audiences, whether it's during International Observe the Moon Night or any day of the week they might be sharing things about the moon. So with that, we are about 30 minutes past the top of the hour. We appreciate, John, you staying on the line for...
Yeah, I'm really glad. I see 35 other participants. I'm really glad everybody else stuck with us, because we could talk about this for hours, right? And then it's time for a burger and a beer. So, but it's fascinating. It's fun stuff. I love working here at NASA.
We so appreciate connecting with all of you educators and informal educators, museum staff, librarians, solar system ambassadors. But most of all, John, I really thank you.
Oh yeah, this is a lot of fun.
Well, great. Well, thank you, everyone. With that, we'll bring this to an official close. And until next time, we look forward to connecting with you again, and have a great rest of your day and a great International Observe the Moon Night.
All right, bye.
Thanks, everyone.